Come along for the ride.
Welcome to the Solar Coaster, the wild ride to the solar industry told by the people living it every day. I'm Anna Covert.
And I'm Alex Herrera.
Solar panels are built to produce electricity for years, but their working life eventually raises a difficult question. What happens when a module reaches the end of its useful service? The answer is not simply to place it in a recycling facility and recover everything inside. Solar panel recycling involves economics, transportation, certification, material separation, and a growing debate over whether some panels described as reusable are actually being moved into overseas waste streams. Today, we will examine those issues through the experience of Solar Panel Recycling, or SPR, and its chief executive, Brett Henderson. The central question is straightforward. Can the solar industry build a recycling system that is both technically credible and economically scalable?
One reason this question is complicated is that the most valuable material in a solar cell is present in a very small quantity. A May 2026 research paper cited in Science Bulletin found that silver represents roughly 0.5% of a solar cell's mass, while accounting for 47% of its recycling value. That imbalance helps explain how recyclers think about end-of-life panels. A panel is mostly glass, and glass has to be recovered cleanly if it is going to be used by glass manufacturers at meaningful volume. At the same time, small quantities of valuable metals can strongly influence the economics of the process. The recycler, therefore, has to handle a material that is physically bulky, costly to transport, and not uniformly valuable.
SPR grew out of an electronics recycling company that had been operating for about 2 decades. The parent company was certified under R2v3 and E-Steward standards, and Henderson said it had followed those standards for roughly 16 years. But he described a concern specific to solar modules. In his view, a solar panel is effectively a single line item for a recycler, and its mostly glass composition can make it a negative value material to process. His concern is that R2v3 Appendix G still allows recycling to be outsourced while a company retains the certification. Henderson argues that for solar, the glass should be recovered cleanly without commingling and by the certified company in-house. That is a stricter interpretation of what certification should demonstrate.
The certification question is especially relevant because a key deadline is approaching in January 2027. SPR's North Carolina operation was described as still being undecided about whether to pursue Appendix G. Henderson said the company had until 2027 to make that decision. He also explained that SPR was building a standalone solar building in North Carolina and expected that facility to be completed before the deadline. Because it would be a separate solar company, he said the facility would not necessarily have to operate under Appendix G. The practical impact of that decision depends on the expectations of customers. If asset owners require the certification in a request for proposals or as a condition for becoming an approved vendor, the standard can matter greatly. Without that requirement, a standalone solar recycler may face little direct pressure to obtain it.
That distinction points to a broader issue in the market. Standards can exist on paper, but their influence depends on whether project owners, engineering firms, operations and maintenance providers, utilities, and other buyers use them when selecting recycling vendors. Henderson said that at the time of the interview, major U.S. engineering, procurement, and construction companies, operations and maintenance providers, and utilities were not requiring the standard. For that reason, he did not expect recycling volumes in the United States to be affected if a meaningful share of the industry missed the deadline. His explanation was that recyclers are demanufacturing a product rather than manufacturing one, so the certification deadline would not automatically determine the amount of material entering the recycling system.
At the same time, Henderson indicated that the industry is actively discussing a different approach. He said a number of people on a committee had been working for about 18 months to develop what could become a gold standard process through a major U.S. trade association. According to his description, the committee's general view was that solar needed a standard written specifically for the industry, rather than relying on a general electronics standard with an added appendix. That does not resolve the certification issue, but it does show why the debate continues. Solar modules have their own material composition, their own logistics, and their own recovery challenges. A standard designed for electronics recycling may not answer every question about clean glass, panel demanufacturing, or the treatment of used modules.
Another question concerns the performance numbers associated with SPR's process. An IEA PVPS Task 12 report cited recovery figures of 99% for copper and up to 98% for silicon. Henderson characterized the basis for those figures as a hybrid of company information and third-party testing. He said the IEA did not require SPR to send samples directly to the organization or to an independent laboratory for confirmation. However, during its questionnaires and interviews, the research team recommended seeing third-party laboratory results and wanted to understand SPR's processes. Henderson said SPR does have tests supporting the figures, while also clarifying that the IEA itself did not send samples to a lab or produce its own laboratory report for those numbers.
That distinction matters because recovery rates can be interpreted in different ways. A number may describe a result observed in a particular process under particular operating conditions using a particular material stream. It does not automatically describe every recycling facility or every type of panel. It also does not tell us by itself whether recovered materials are clean enough to be consumed at industrial scale. In the case of solar modules, the quality of each separated commodity is central. A high recovery percentage is useful only if the recovered copper, silicon, glass, and other materials can move into appropriate downstream markets. SPR's position is that clean separation is the essential technical challenge.
Henderson drew a sharp contrast between two mechanical approaches. One approach is to batch feed whole solar panels into a shredder, reduce them as a complete assembly, and then try to separate the different commodities afterward. He said this type of processing will always lead to contaminated products. SPR's approach is described as mostly mechanical, but systematic. Instead of treating the full module as one object to be shredded, the company removes each commodity in sequence. The goal is to separate the layers that include glass, encapsulant, silicon, and backsheet while keeping the resulting materials clean. Henderson said SPR had invested $12 million in new glass technology during the year discussed in the interview, with the specific challenge of separating encapsulated glass and the other layers.
The emphasis on glass is understandable. If recovered glass contains plastics, silicon, silver, or other metals, it may not be usable by glass manufacturers at volume and scale. In that situation, the recycler may recover a large amount of glass by weight, but still fail to create a commercially useful feedstock. Clean separation, therefore, links the technical and economic sides of the business. Better separation can improve the value of recovered materials, but achieving it requires equipment, labor, and capital. SPR's approach depends on continuing investment in technology, and it also depends on having enough material moving through the network to justify that investment.
SPR said it is profitable from recycling alone, provided asset owners pay some level of recycling fee, but that fee has changed substantially since the company began in 2018. Henderson said it had fallen by almost 80%. He attributed that reduction mainly to continued investment in two areas: technology for cleaner separation and the logistics of moving panels across the United States. The company operates in a country with a large geographic footprint, so transportation is a major cost. This is a reminder that recycling economics cannot be evaluated only by looking at the value of silver, copper, silicon, or glass. A panel has to reach a facility, and the recovered commodities then have to reach their next users.
Henderson identified transportation as the biggest cost driver in the U.S. solar recycling market. His proposed response is a distributed network of owned and operated recycling facilities. More facilities located closer to the material supply would reduce the distance panels need to travel. He also pointed to another opportunity: more clean glass entering the U.S. market and remaining within regional markets. In his view, the largest factor in reducing costs further is volume. He summarized the idea in familiar recycling industry terms: volume is king. As throughput increases, fixed investments and operating systems can be spread across more panels, while regional networks can reduce transportation burdens.
The market for panel reuse creates another layer of complexity. Henderson described what he sees as significant greenwashing in global reuse activity. His concern is that some panels are offered as reusable, then shipped overseas to destinations including Southeast Asia or the west coast of Africa. The economic motivation can be powerful. Aluminum prices are high enough that a company may take panels from asset owners at no charge while presenting the transaction as reuse. If the panels are later exported, the shipping costs can be absorbed and labor costs may be limited or absent. A container can hold approximately 500 to 550 modules. Those conditions create an inexpensive path for moving panels across borders under the label of reuse.
The difficulty is that the reuse market is, in Henderson's assessment, nowhere near a scalable level. He highlighted regulations governing the connection of used panels back to the electrical grid. In the United States specifically, he said the UL rating is no longer valid once a panel becomes used. That does not mean every used panel has no possible application, but it does mean that returning used modules to grid-connected service involves regulatory constraints. When the economics of aluminum, shipping, and limited labor are combined with those constraints, a shipment described as reused may not represent a durable second life market. It may instead move panels away from the original owner without establishing a reliable pathway for their future operation or recovery.
SPR reportedly receives 10 to 15 inquiries each week from companies seeking to buy reused solar panels, which Henderson described as a sign of strong interest rather than proof of a mature market. The key question is what happens after the panels leave the original system. If a used module cannot retain its relevant certification for grid connection, and if regulations limit where it can be installed, then a claim of reuse needs careful examination. The distinction between genuine second life deployment and overseas movement of unwanted equipment is important for asset owners, recyclers, regulators, and communities receiving the panels.
Taken together, the issues point to several tests for the solar recycling industry. First is certification. Standards need to make clear who actually performs the recovery and how cleanly the materials are separated. Second is evidence. Recovery rate claims are more useful when their testing methods, samples, and conditions are transparent. Third is economics. Recycling fees, technology investment, transportation, and commodity values all determine whether a facility can operate profitably. Fourth is scale. A process may work technically, but a national system requires enough volume and enough regional capacity to control logistics costs. Finally, reuse claims need to be evaluated against the regulations and certifications that govern used panels, especially when modules cross international borders.
The situation described by SPR does not produce a single simple verdict about solar panel recycling. It shows an industry trying to build infrastructure while material values, standards, and end markets are still developing. Silver can represent nearly half of a cell's recycling value, despite being only a small fraction of its mass. Glass can make up most of the physical material while remaining difficult to transport and valuable only when it is clean. A certification deadline can encourage consistency, yet a general standard may not fully reflect solar-specific needs. And a growing interest in reuse can either support longer equipment lives or conceal a less accountable export pathway.
The practical lesson is that end-of-life planning has to begin before panels are removed from a site. Asset owners need to understand the recycler's process, the destination of each recovered material, the evidence behind recovery claims, the role of third-party testing, and the transportation plan. They also need to distinguish a recycling fee from the value of recovered commodities and to ask what certification is required by their contracts or procurement processes. For recyclers, the challenge is to keep investing in separation technology and regional capacity while the fee structure changes. For the industry as a whole, the challenge is to develop standards that reward transparent, clean, and genuinely scalable recovery.
Solar power is often discussed in terms of deployment, generation, and manufacturing. The end-of-life stage is less visible, but it will become more important as the installed base ages and more modules are removed. The choices made now will influence whether recovered glass becomes a useful industrial input, whether valuable metals are captured, whether panels are transported efficiently, and whether reuse represents a real service or simply delays responsible disposal. The experience described by SPR suggests that the central issue is not just whether a panel can be processed. It is whether the entire chain, from collection to separation to final market, can be verified and operated at scale.
That brings us to the main conclusion. A credible solar circular economy requires more than a label saying recycled or reused. It requires clear standards, documented testing, clean material streams, realistic logistics, and a market capable of absorbing what facilities recover. The January 2027 certification deadline may become one point in that development, but it will not by itself determine the future of recycling volumes in the United States. The larger questions are whether the industry adopts solar-specific standards, whether asset owners demand them, whether recycling networks become more regional, and whether reuse claims reflect actual compliant deployment. As solar expands, the quality of its end-of-life system will become part of the technology's overall value.
I'm on a solar coaster. Come along for the ride.
This episode of The Solar Coaster is narrated using AI-generated technology, representing Anna Covert and Alex Herrera. The material presented is aggregated from publicly available solar industry news sources. All commentary reflects reported industry developments and does not constitute personal opinions, investment advice, or endorsements by the hosts or
Solar
producers.
Coaster is proudly sponsored by Sun Energy Today, redefining what solar means for business and infrastructure. We engineer and deliver large-scale clean energy solutions, from megawatt solar farms to advanced graphene storage, designed for resilience, performance, and measurable return. Sun Energy Today, built to power what's next. Learn more at sunenergytoday.com.